You know that beautiful, predictable curve a ball makes when you toss it to a friend? It's this graceful arc we see absolutely everywhere. It's like a silent dance that objects perform in the air. So let's dive in and unpack the physics behind that perfect curve. And that really is the big question here, isn't it? Why is that path so consistent? I mean, you could be talking about a baseball, a soccer ball, even water shooting out of a fountain. They all seem to follow the exact same fundamental script. So what's the secret behind this universal motion? And seriously, once you start looking for it, you see it everywhere. From something as simple as throwing a ball to the powerful launch of a kicked football. Even something as intense as a bullet fired from a gun, they all trace the same signature curve. It's got to be one of the most common physical things happening in our world. Well, physics has a name for this, of course, projectile motion. Now, the key to this definition is its simplicity. The path is shaped by one force, and one force only, gravity. Now, for this perfect model, we're going to ignore other stuff like air resistance. It's a pure contest between that initial launch and the constant pull of the Earth. So how in the world do we decode this curve that looks pretty complex? Well, here's the brilliant insight that just unlocks everything. We don't have to analyze it as one complicated movement. The secret is to see it as two completely separate, much simpler motions that are happening at the exact same time. Let's break that down. On one hand, you've got the horizontal motion. That's the object just cruising forward at a steady, constant speed. No drama there. But at the same time, you have the vertical motion, the object moving up, slowing down, stopping for just a split second at its peak, and then speeding up on its way back down. These two journeys are totally independent, but when you put them together, you get the parabola. Okay, so let's focus on that vertical journey first, because honestly, that's where all the action happens. What's causing the object to slow down as it goes up and then speed up as it comes down? Well, it's all thanks to a single relentless force. And that force is gravity, which we represent with this number, g. It's a constant acceleration of 9.8 meters per second squared, always pulling straight down. Every single second an object is in the air, gravity is chipping away at its upward speed by 9.8 meters per second. And once it starts falling, it's adding to its downward speed by that exact same amount. It's like the constant director of this whole vertical dance. All right, now let's talk about the other piece of the puzzle. We're going to shift our focus to the horizontal journey, which you'll see is a lot, and I mean a lot, simpler. Right, so the crucial point here is that once the object is launched, there's nothing pushing or pulling it sideways. It's just coasting. That initial forward push it got at the very beginning is all it has. So its horizontal speed stays exactly the same from the moment it leaves your hand to the moment it lands. Just a steady, predictable cruise. Okay, so this is where it gets really cool. Now that we've separated the motion into its two simple parts, you've got the constant horizontal cruise and the gravity-controlled vertical trip, we can start making some seriously powerful predictions. We can use the language of physics to calculate exactly what that projectile is going to do. Let's start with a really practical question. If you launch something, how long is it actually going to be airborne? Physicists call this the time of flight, and it turns out it depends entirely on that vertical part of the journey. And the formula for it really shows you how it works. It's basically a battle. The top part, that 2u sine theta, that represents how much initial upward velocity it has. U is just the launch speed, and sine theta helps us figure out just the upward part based on the angle. And on the bottom, you have g, gravity's constant force pulling it back down. So the stronger that upward launch, the longer it flies. Simple as that. Okay, next logical question. We know how long it's in the air, but what about the peak of its journey? What's the absolute maximum height it's going to reach before gravity finally wins the fight and starts pulling it back down to Earth? And again, the formula shows us it's another showdown between the launch and gravity. The max height depends on the square of that initial upward velocity. That's the u squared sine squared beta part. And squaring it means that even a little more upward push gives you a lot more height. And all of that is fighting against 2g, or double the force of gravity. It's the perfect way to measure how high the object can possibly climb before it just runs out of steam. And finally, the question everybody wants to know, especially if you're into sports. How far is it going to go? What's the horizontal distance it will travel? This is the range, and it's where both the horizontal and vertical motions come together to decide the final landing spot. Now check this out. The range combines everything.
It depends on u squared, the initial speed squared, so launch speed is obviously critical. But it also depends a ton on the launch angle, which is what that sine 2 theta is all about. And theta, by the way, is just the symbol for whatever angle you launch it at. And of course, the whole thing is limited by g, gravity, pulling it down. This is the exact formula that tells us why, in a perfect world with no air resistance, a 45-degree angle will give you the absolute maximum distance.
So after all those equations, let's just bring it back to this simple, perfect summary. It really boils down to this. An initial push sends it forward, while gravity is constantly pulling it downward. The combination of those two simple actions creates that perfect, predictable, parabolic curve every single time. But let's end on a puzzle. If our perfect physics model proves that 45 degrees is the magic angle for maximum distance, why don't we see that in the real world? Why do elite athletes, like shot putters or quarterbacks, release at a lower angle, maybe closer to 35 or 40 degrees? What real-world force are they accounting for that our perfect little model leaves out? That, right there, is where the simple physics gets really